Next, I want to talk about maps as a model of reality. So one thing to think about, probably one of these big picture things to consider when we're learning about GIS is that when we're trying to answer many questions, it's too complex to analyze the actual world itself. So what we do is we need to reduce the complexity in order for us to get our arms around it and do the analysis that we want. So part of what so you have a real world here, you have this swamp, you want to understand certain aspects of this wetland or swamp. We need to have some type of data model where we represent it in a way that the computer can understand. And so what we're doing is we're actually taking the real world, using our software to, and then, at the very basic level, the computer is understanding this in its base computer code, and then we use software to so that we can visualize it and work with it in a practical way. So what we're really doing is we're selecting the most relevant features for our geographic question, and then likewise ignoring others. We really want to, kind of filter out filter out the unnecessary part of the real world and focus on the parts that are necessary for answering our geographic question. And then we want to generalize those features in a way that they can be represented in a GIS. And there's kind of two major ways that we can do that. One is called vector, where we use geometry, and the other is called raster, where we use a grid of cells. And so what I want to talk about next is those two data models, whether we represent them as, sometimes we call it objects, like geometric features, or what we call fields, a grid of information, vector versus raster. And this is a key learning objective in this class, so we will kind of be discussing it as we go throughout the semester. So let's go over that. Let's beat this to death a little bit. So one way to represent the reality is through discrete geographic features or objects. We call this the vector model. And these are some examples of using vector versus raster. So there are three basic types of vector or geometric features that are used in GIS. One are points. Points have an X and a Y coordinate. So if you remember from geometry, the Cartesian coordinate system where you have an X and a Y, that's how the computer stores this information, that it has a bunch of like a list of features, like with an X and a Y, and it's able to represent that as a point in the system. These might be fire hydrants, housing addresses, any kind of discrete point features. Some are better represented by lines. So this might be highways or streams. In GIS, we often call these polylines because rather than one single line, there are a series of connected lines. So you can imagine a stream, you can't really make one line. It'd be a series of connected lines that would have the shape of the stream. And then areas, and we call these polygons in GIS speak. And these are areas. So here's another way to think about it, that you have the most primitive part, or the most basic element, is points, locations of things, latitude and longitude, or a projected coordinate system. And if you can connect up these points to make lines or polylines, right? Now these lines can then enclose information like an area, and we call these a polygon. So counties, housing parcels, congressional districts, soil map units, vegetation boundaries, these can be represented by these enclosed areas that are called, we call them polygons. So here a polygon is made up of these 4 points, and the lines of these points enclose an area we call a polygon. So here's another way of looking at it. We have points, perhaps these three trees are represented as points. We have a series of coordinates, a pair of coordinates for each one, here, here, and here. Now, in this example, if we want to also represent this stream, we have a set of points that are connected together like a list of points that make up what we call a polyline. A polyline meaning a collection of lines that make up a feature. Right? Now we have this pond over here, but that one is probably best represented by a series of points that make a line that enclose an area, also known as a polygon. These have different things that we can understand about them. For the points, we can know their x coordinate and their y coordinate. For a line, we can know the length of the line. And for an area or polygon, we know the area. We can calculate the area of that polygon. We can know how much area, how many square meters does that stream make up, or that lake make up. We can understand how many kilometers is that stream. That the computer can calculate for that for us because it can do the math for us. So again, here's the concept. We have this X and Y coordinate system. The units of the coordinate system would be in meters or sometimes feet. This would be a real world coordinate system where each number is a number of meters or feet in a projected coordinate system. A projection coordinate system is where we take the round Earth and we flatten it out, like in the examples we talked about last week in the video with the beach ball, where they're trying to stretch the map and turn it into a flat coordinate system. And so here we have a set of coordinates, and these are just small numbers as an example that enclose a polygon. Here's some other examples with some imagery underneath. These are a couple of polygons, and we can calculate the area of each one. And it can also, and these features will be tied to attribute tables. So here we have some points on the map. And for each of these points, there is a database record. So this is ID, this is a real fire hydrant in real life. This is the X and Y location of the fire hydrant, so we can display it on a map. And then here is a database record. It says how many flanges it has, the color of the fire hydrant, and the rating of the fire hydrant. So we have both spatial information and database information attributes to represent a feature in real life. Now, the second way we can represent information is through, and we're looking at the bottom part here, continuous spatial data. We call this raster. Using pixels like in a digital photo. It's represented as a grid of values. And the type of data this is used most for are things that are continuous in nature, like a grid of elevation values or a grid of temperature. A digital elevation model where each little cell represents the elevation, population density at each little cell, etc. By the way, imagery like satellite imagery or aerial photographs, or even a digital photo, is also this uses this type of data as well. So aerial imagery that aligns with the map is actually raster data that where the values are actually the colors that you see. So here we have a combination of data. We have elevation. So each one of these pixels has a different elevation value. And here we've taken our area, our parcels and our building footprints, and we can overlay them with our elevation values. Here's another example of raster data. This is a color infrared orthophoto. This is like a satellite picture that has multispectral imagery, and we can overlay the two together. Here's another kind of comparison. These are features that are vector. We have points, lines, and area or polygon. And if we were to try to also represent those features using raster, we would make a big grid, and then we would assign grid cells to the points, a series of grid cells as lines, and a series of grid cells as an area. Different ways of, these are different data models that we use in GIS. Each have advantages and disadvantages. We'll talk more about that later. But it kind of depends on what you're using it for. For elevation, raster is better. For streets, vector is better. So raster data, the way it works, it's a grid of values. It's defined by an X, Y, an origin. So it has a lower corner. And then a cell size. How big are those little pieces of the grid? And they're in real world units, like they're either 30 meters or 10 meters or what have you. How big, what's the height and width of each square in real world, real life units? So this is kind of the way it works. You have and this is small to make it kind of simple to understand. In real life, they'd be like thousands and thousands of these cells. But in this example, you have this, small grid. We would know the coordinate of the lower left cell in X and Y. And we would know how many meters or feet, how high and tall each of these cells are. And then knowing that, let's just overlay this with other spatial information. Here they have the resolution depends on how big the cells are. So here this is 4 cells with 100 meters each, 100 meters wide and tall. If we made it more detailed, it could be 50-meter cells, 50 meter wide, 50 meters tall, but then we'd have 16 cells instead of 4. One thing to note, that each time you cut the cell size in half, you have 4 times as many cells. So the size of the data really escalates quickly as you make them more detailed. Let me move myself down there. This one has 25-meter cells, and then we've quadrupled it now to 64 cells. And we can see the effect of this on the next image. If we're looking at like aerial photography or satellite imagery, these are different resolutions. This is where the data is 0.5 by half a meter by half a meter, very detailed. Although at this scale, we can't really tell much difference. 1 by 1 meter, 2 by 2 meter. Now at 5 by 5 meters, starting to look a little bit more blurry. 10 by 10 meter, blurrier. Now it's really kind of hard to make out at 20 by 20 meters, 40 by 40 meters, and then by 80 by 80, we don't know what's going on anymore. Here's another example. And as we increase the cell size, we have smaller files, but we have less detail. So it's a trade-off. You don't want to have too much detail because, like, if you look at these top 3, the third one probably does just fine without having extra information. But as we get, at some point, we're like, well, that's getting too not enough detail for what we want to do. All right, and so let's just kind of look back at this figure. We have, let's say we have home addresses in a vector model. These would be represented by geometric points. Here's a transportation network that's represented by polylines. Here's parcels that are represented by areas or polygons, we call them. If we were using raster, this would be a grid of information where each cell, the cell would be either yes or no for the point values. These are lines that would be represented by the cells connected to each other to form a line, like pixels. Or we could have pixels that are turned on or turned off for the areas. And so that's just a brief introduction to vector, different data models, vector versus raster.